Hello, this video is a continuation of solving exponential and logarithmic functions. This slide and the slide after about exponential equations is a reminder slide about which part of the exponential equation is unknown and the key strategy to go about to solve for the unknown. This is the reminder slide about logarithmic equations. Use either the bullet-pointed ideas here or the flowchart given previously to help you strategize techniques for solving exponential and logarithmic equations. One strategy that we discussed previously is taking the log of both sides of an exponential equation. This becomes especially important when the two bases of the exponential equations cannot be rewritten with the same base. However, I can do anything I want to an equation so long as I do the exact same thing to both sides. This strategy is taking the log of both sides. I get to choose which log I want to take. Whatever base I choose on one side, I keep the base on the other. A smart strategy would be to choose a log that I can easily evaluate either in my calculator or in my mind. Most easily with logs, especially with different bases, would be either the common log with base 10 or the natural log with base e, so long as I apply the same to both. Throughout this lesson, you'll see me exchange with both. As you can see in both the key concept and in the example, it does not matter which base you choose so long as you apply the same base to both sides. In this first example, 3 to the power of 4x minus 1 equals 7 to the power of x plus 1. I'm going to apply the log base 10 to both sides of the equation. Because I applied the same function to both sides, the equivalence of the equation is maintained. The reason we applied a log to both sides is because now we can utilize log properties which say the exponent can be multiplied to the front of the logarithm. The exponent 4x minus 1 and the exponent x plus 1 both drop to the front of their respective logs. Be careful when dropping these to the front to keep parentheses around the exponents, as these are expressions. At this point, I have each expression being multiplied by some number. Remember that log of 3 and log of 7 are just some numbers, which you can actually approximate in your calculator. We won't pick up the calculator until the very last step when we have finally isolated x. At this point, an expression being multiplied by a number, we now have to distribute the number into each part of the expression. The log of 3 is distributed, and log of 7 is distributed respectively. Again, remember, each of these expressions with log are just numbers. Log of 3 and log of 7 are numbers that are being multiplied to our variables, or are terms that are being added or subtracted. As you would with any equation, you need to have your variables on the same side. In order to do this, I will now subtract x log 7 from both sides and add log 3 to both sides. Remember that you cannot combine 4x log 3 and x log 7. They are not like terms. So in my next line, these will be two individual terms. Likewise with log 7 and log 3. Now, although you could simplify log 7 plus log 3, two logs broken apart by addition you can combine with multiplication, it is not really necessary. So why do an extra step that I don't need? At this point, I see on the left side of my equation that I have my x stuck in two different terms. In order to pull out the x, I will factor it out from the left side of the equation. Now that I have factored out the x, I have x now being multiplied by some number, the sum number being represented by 4 log 3 minus log of 7. Well, to undo the multiplication happening on x now, I need to divide both sides by this logarithmic expression. So now divide both sides by the 4 log 3 minus log 7. Although we don't know the exact values of these expressions, any expression divided by itself, we know, just simplifies to the value of 1. This has now isolated our x on the left side of the equation. On the right side, we just have a messy but long log expression. Log of 7 plus log of 3 being divided by 4 log of 3 minus log of 7. This is our exact answer for the solution of this exponential equation. However, we will carefully type this into our calculator to have an approximated answer and round to 3 decimals. Remember to be very careful to close parentheses after each log. We want to take the log of 7 alone, not the sum. Here's the expression typed into the calculator. Note that we used the common log, base 10, to solve this equation. If you used the natural log, you would type in the very similar expression with natural log. Note with both log base 10 and the natural log are two good options because there are buttons on my calculator. I do not need to use the change of base formula. We can approximate the value of x as approximately 1.243. Now to check my work, as we always want to check our solution, we want to tell our calculator to store this value in for the variable of x in order to keep the most exact answer as possible. Here I have stored the value in for x, and now I am carefully typing the original problem, 3 to the power of 4x minus 1, and seeing if that truly does equal the right side of the equation, 7 to the power of x plus 1. Remember that there is a test feature in your calculator where you can pull up the equation symbol, hitting second math. Because the problem was an equation, we will choose option 1, which is equation, and type the right side of the equation in. This feature of the calculator will either spit out a 1 if the statement is true for the given value of x, or a 0 if the statement is false for the given value of x. Since the calculator has returned the value of 1, this means the value that we have plugged in for x keeps both sides of the equation equivalent to one another. Therefore, the value of x that we have is indeed a solution to the exponential equation. Let's try another example. Note on this first example on the left, there is much more happening to the exponential part of our equation. Before we can do anything, we must isolate the exponential part of our equation first. In this case, we will subtract 1, then multiply by 3/2 on both sides. Now I see I have an exponential equation with unlike bases. I will choose to apply a log to both sides of the equation. Again, it does not matter which log I choose. Let's choose the natural log this time. By applying the log to both sides, I can now drop the exponent using the power rule of logs. Remembering to keep this expression together with parentheses, which will then remind me in my next step that I will now have to distribute the natural log of 2, which is just some number, to this expression. My goal is still to isolate the variable x. I need to subtract off this value, natural log of 2, from both sides. Then I need to undo the -3 and natural log that are happening on the x. Both -3 and natural log of 2 are being multiplied to x, so we will divide both sides by -3, natural log of 2. Note, -3 divided by itself is just the value of 1, and natural log of 2 divided by itself is also just the value of 1. I have now successfully isolated x from one side of the equation. On the other side, I have a logarithmic expression, natural log of 9 minus natural log of 2, all over -3 natural log of 2. If you chose a different log, like the common log, your expression will look different, but the values, when we approximate them, will be the exact same. Using the calculator to approximate this expression, we have that x is approximately -0.723. Again, use the store feature of the calculator and test to see if x equals this expression actually makes the equation true. As we've stored the value of x into our calculator and typed in the original equation, and my calculator has returned the value of 1. That means this true value of x is a solution to this equation. Try the next problem on your own. Here's the work for that problem. How did you do? Exponential equations can also show up within a quadratic form. Look at the example here. 5 to the 2x power minus 6 times 5 to the x power plus 5 equals 0. Well, if u is substituted in for everywhere 5 to the x power is seen, notice how this looks strikingly like the quadratic equations you are so used to solving from before. This is the strategy we will use to solve such problems. Note that 5 to the 2x power can actually be rewritten as 5 to the x raised to the second power. This is where the u squared aspect of this quadratic form is coming from. As a strategy, you may choose to use another letter, like u, in place of the exponential part, or you may choose to use a symbol, such as a heart or any other symbol of your choice, that might be easier to deal with rather than another variable. Be very careful choosing x. We like to use x in our equations, and that will get very confusing very quickly. So do not use x. Use some other letter or symbol, or try to work with the exponential part as it is, as we're solving these quadratic formed equations. Take a look at this quadratic equation. Note that I can rewrite the first term, 10 to the power of 2x, instead as 10 to the x power squared. If you choose to use a letter or a symbol to represent the exponential part, this is where you will define it. If I use a symbol, I generally like to use a heart so I don't get confused with letters. I'm going to let heart represent the value 10 to the x power, so that anywhere I see a 10 to the x power in my equation, I will now replace it with the heart. Note that it is important to define our symbol and what it represents. Now when I have plugged in the heart, I have something squared minus 12 times something plus 20 equals 0. This is, in our most essence form, the quadratic equation. To solve this, I would like to try to factor numbers that multiply to 20 and add to negative 12. Negative 10 and negative 2 multiply to 20 and add to negative 12. Now for the first parts, what multiplies to heart squared? Well, of course, it's heart times heart. Now that I have factored the quadratic form of the equation, I have now been able to use the zero product property. I have two expressions that are multiplied to equal 0. The zero product property indicates that either one of those equations could equal 0. That means heart minus 10 can equal 0, or heart minus 2 can equal 0. In this case, heart would equal 2, or heart can equal 10. However, that is not what the problem asks. I didn't want to know what heart's value was. I need to know what x's value is. Remember that heart is a placeholder for the value of 10 to the x power. The value of x here must be 1, using the one-to-one property of exponentials. On the second side, instead of heart equal to 2, I really have 10 to the x power equals 2. Well, this side is not as nice. I have two unlike bases with an exponential. Here's where we use that same strategy that we did in example 1. Apply a log to both sides and simplify. Here I apply the common log to both sides. This allows me to drop the variable exponent down to the front using log properties. But I chose the common log over the natural log here because when I've dropped the variable exponent down, log of 10 is really just the value of 1. So I really already have x isolated. The value of x is just the log of 2, which approximates to the decimal 0.301. I can use the store feature and check both values of x into the original equation. Both x equals 1 and x equals log of 2 are solutions to this problem.